In the endless silence beyond our solar system, NASA's Voyager 1 has just done the impossible. On May 12, 2025, the probe caught a continuous plasma hum rippling through interstellar space. A signal so steady, so out of place, it defies every pattern we've learned from flares, bursts, or cosmic static. That's not just a technical achievement by a 47-year-old spacecraft now 24 billion kilometers from Earth. It's the first time we're truly hearing the voice of the void. What is this cosmic whisper, and what does it reveal about a universe we thought we understood? To answer that, we need to follow Voyager back to the moment its journey began. September 1977 arrived with a narrow window, one that wouldn't open again for another 175 years. For engineers at NASA's Jet Propulsion Laboratory, the math was as daunting as it was irresistible. 4 giant planets, perfectly aligned for a single flight path, each offering a gravitational boost to the next. This rare planetary configuration, first charted out in the 1960s, promised a kind of cosmic slingshot. If a spacecraft launched at just the right moment, it could ride the gravity of Jupiter, Saturn, Uranus, and Neptune in sequence, completing what scientists called the Grand Tour. No previous mission had ever attempted such a leap. The calculations demanded precision to the second. A delay of even a few months would cost decades, or force a compromise that could never be recaptured. The solution was bold. Not one probe, but 2, Voyager 1 and Voyager 2, each with a unique trajectory, each designed to maximize the fleeting opportunity. The dual probe strategy wasn't just about redundancy, it was about ambition. Voyager 2 would launch first, on August 20, 1977, taking a slower, longer route that allowed for a possible Uranus and Neptune encounter. Voyager 1, with a more direct path, would follow on September 5th, aiming for the closest, most detailed look at Jupiter and Saturn ever attempted. The timing was critical. The launch window, calculated to fractions of a degree, meant that even minor technical delays could have forced the cancellation of the entire mission. Every decision, from the rocket's fuel load to the sequencing of onboard computers, was shaped by this brief alignment, an event that last occurred when Thomas Jefferson was president. Engineers faced a daunting challenge: build a spacecraft tough enough to survive years in deep space, yet nimble enough to seize fleeting moments at each planetary flyby. Voyager's design reflected this tension. The bus-sized main body carried 10 scientific instruments, each with its own power and data needs. A 3.7-meter high-gain antenna would beam Discovery's home across billions of kilometers, while 3 radioisotope thermoelectric generators supplied the electricity. At first, a robust 470 watts, but destined to fade with every passing year. Redundancy was built in wherever possible. Each major system had a backup, from the command computers to the thrusters that would steer the craft during critical maneuvers. Even the software was designed to be updated from Earth, with commands encoded in binary and transmitted by radio waves that would take hours to cross the void. The stakes were enormous. If Voyager missed its first planetary target, the chain reaction would collapse. The gravity assist from Jupiter was not just a shortcut, it was the only way to reach Saturn, and beyond that, the outermost planets. The mission's architects had to plan for every contingency, knowing that once launched, there would be no second chances. The margin for error was vanishingly small. The entire mission, decades of planning, billions of dollars, and the hopes of a generation, rested on the precision of a single moment in September 1977. Yet beneath the technical rigor lay something deeper, a sense of daring. Voyager's planners were betting not just on their calculations, but on the ability of human ingenuity to stretch limited resources across an unprecedented journey. The probes would carry less fuel and fewer spare parts than any deep space mission before them. Every gram was weighed, every circuit tested, every command pre-scripted for events years in the future. The team knew that the further Voyager traveled, the fewer tools they would have to fix what might go wrong. But the chance to unlock the secrets of the giant planets and to send a machine hurtling toward the edge of the sun's domain was too rare to pass by. As the countdown ticked toward zero, the world watched a rocket rise from Cape Canaveral, carrying with it the most ambitious deep space mission ever attempted. For the engineers and scientists behind Voyager, the launch was both an ending and a beginning. The grand tour had started, and with it, a new chapter in humanity's exploration of the cosmos. Jupiter's swirling clouds filled the cameras in March 1979, but it was a moon, Io, that stole the show. A plume, rising 300 kilometers above the surface, caught the attention of navigation engineer Linda Morabito. She had been enhancing images to track Voyager 1's position, but what appeared was unmistakable: an active volcano erupting in real time. Until that moment, volcanic activity had never been seen beyond Earth. The discovery forced scientists to rethink what was possible for moons orbiting the outer planets. Io's surface, scarred by sulfur and dotted with smoking calderas, revealed a world in constant upheaval, shaped by tidal forces from Jupiter's immense gravity. Europa, another Galilean moon, offered a different kind of mystery. Voyager's cameras captured a surface crisscrossed with dark fractures, evidence of a thick shell of ice. No impact craters, just a smooth, unbroken crust, hinting at something dynamic beneath. The patterns looked like the cracked skin of a frozen lake in spring. Scientists began to suspect that beneath Europa's icy shell, a liquid ocean might exist, kept warm by the same tidal flexing that drove Io's volcanoes. The possibility of water so far from the sun shifted the search for life to places no one had expected. Jupiter itself revealed more than anyone had anticipated. The Great Red Spot, already famous, turned out to be a vast, centuries-old storm, larger than Earth. Voyager's instruments mapped the planet's powerful radiation belts and measured wind speeds exceeding 600 kilometers per hour. The planet's faint ring, a surprise in its own right, appeared as a thin, dusty arc, nearly invisible from Earth. Each image and data stream upended old assumptions, turning Jupiter from a blurry disk in telescopes into a complex, turbulent world. By November 1980, Voyager 1 approached Saturn. The rings, once thought to be simple, resolved into thousands of narrow bands, some only a few kilometers wide. Bright gaps and braided strands hinted at unseen moons, shepherding the icy debris. The planet's atmosphere, composed mostly of hydrogen, rotated every 10 hours and 39 minutes, with bands of clouds stretching across its surface. Saturn's largest moon, Titan, became a prime target. Voyager 1's trajectory was chosen specifically for a close flyby, sacrificing the chance to visit Uranus and Neptune so that the probe could pass just 4,000 kilometers above Titan's surface. Titan did not disappoint. Voyager's instruments detected a thick, orange haze, an atmosphere denser than Mars's, composed mainly of nitrogen with traces of methane and ethane. Sunlight barely penetrated to the surface. The probe's radio signals measured the atmosphere's depth, confirming that Titan was the only moon in the solar system with a substantial gaseous envelope. Hints of organic molecules in the haze suggested complex chemistry, possibly resembling the early Earth before life began. In total, Voyager 1 returned over 16,000 images during its Saturn encounter, mapping not just the planet and its rings, but a retinue of moons, each with its own story. The success at Jupiter and Saturn transformed Voyager 1's reputation. No longer just a flyby mission, the probe had become an explorer in its own right, rewriting textbooks with every transmission. The cameras, now legends in their own time, would soon be powered down to conserve energy. Ahead lay a new frontier, one that could only be sensed, not seen. But the legacy of these planetary encounters would shape every step that followed, proving that even a machine built for a single purpose could become a symbol of discovery for generations to come. By February 1990, Voyager 1 had delivered more than 18,000 images of the outer planets and their moons. The final photograph, Earth, caught as a pale blue dot in a sunbeam, closed the camera's eye for good. With that, the probe began a new phase, one built not on pictures, but on the invisible. Every watt mattered. The spacecraft's 3 radioisotope thermoelectric generators, each powered by decaying plutonium-238, provided less energy with every passing year, about 4 watts less annually. What started as a robust 470 watts at launch had already faded to under half that. The high-gain antenna alone demanded nearly 200 watts just to keep its beam pointed home. Running all 10 science instruments was no longer possible. The mission team faced hard choices, weighing the value of each experiment against the shrinking power budget. Cameras, once the pride of the mission, were the first to go. Their heaters and electronics were powered down, one by one, to conserve energy for instruments that could sense what lay ahead. The magnetometer, the plasma wave system, the cosmic ray detector. Each of these required just a few watts, enough to listen for the faintest signals from the edge of the sun's domain. The probe's focus turned to fields and particles, trading images for data streams that mapped boundaries no camera could see. The transition wasn't just technical, it was philosophical. Voyager 1, now blind to light, became an explorer of the unseen. It measured the density of charged particles, recorded shifts in the magnetic field, and tracked cosmic rays as they ebbed and surged. Every bit of data squeezed from those waning watts offered a glimpse into the unknown. The mission's survival depended on careful rationing. Commands sent from Earth, taking more than a dozen hours each way, instructed the spacecraft to switch off heaters, cycle instruments, and reallocate power, sometimes at the cost of redundancy and safety margins. Each year, another instrument would be powered down, a quiet retreat in the face of inevitable decay. Yet, even as the power faded, the probe's role grew. Voyager 1 became the first human-made object to sense the approach of the heliopause, the boundary where the sun's influence yields to the interstellar medium. The data it returned, though invisible to human eyes, became the new currency of discovery. The legacy of the cameras lived on in the pale blue dot, but the mission's future would be written in the language of plasma waves and magnetic fields. With every adjustment, Voyager 1 demonstrated a kind of resourcefulness that echoed the ingenuity of its creators, a machine adapting, improvising, and enduring it pressed farther into the dark. Beyond the last planet, the sun's influence does not simply vanish. Instead, it forms a vast, invisible bubble, an envelope shaped by the constant outflow of solar wind. This region, known as the heliosphere, stretches for billions of kilometers in every direction, carving out a protective zone that shields the solar system from much of the galaxy's harsher radiation. At its center, the sun releases charged particles at supersonic speeds. These particles race outward until, at a certain distance, they begin to slow. The point where the solar wind abruptly drops below the speed of sound is called the termination shock. For Voyager 1, that boundary lay more than 13 billion kilometers from the sun. Here, the solar wind thickens, heats up, and grows turbulent, forming a region known as the Helios Heath. Within this buffer, the solar wind and the interstellar medium begin to mix, their boundaries blurred by waves and eddies, on a scale larger than any planet. But the true edge of the Sun's domain comes farther still. The heliopause marks the place where the outward push of solar particles is finally balanced by the pressure of interstellar gas. On one side, the solar wind dominates. On the other, the plasma between stars takes over. This boundary is not fixed. It breathes in and out with the Sun's activity, swelling during periods of high solar wind and shrinking when the Sun quiets down. For Voyager 1, crossing the heliopause in 2012 meant leaving behind the last traces of solar wind and entering the realm of interstellar space. The environment beyond is colder, denser, and governed by the magnetic field of the Milky Way rather than the Sun. Inside the heliosphere, space is not empty. The solar wind fills it with a thin plasma, carrying magnetic fields and energetic particles outward. These fields twist and spiral, shaped by the Sun's rotation and the occasional violence of solar storms. Cosmic rays, high-energy particles from distant supernovae, are deflected or slowed by this bubble, making the space inside less hazardous than the galaxy beyond. The heliosphere serves as a shield, but also as a laboratory, a place where the boundaries between solar and galactic forces can be studied directly. For decades, the exact size and shape of the heliosphere remained a matter of debate. Models predicted a teardrop, a comet-like tail, or even a sphere, but only direct measurements could resolve the question. Voyager's journey provided the first hands-on map of these boundaries. Each transition, termination shock, heliosheath, heliopause, marked a new chapter in the probe's mission. The stakes were clear. Only by crossing these invisible frontiers could scientists test their models and glimpse what lies between the stars. The heliosphere, once a theoretical construct, became a measurable, dynamic structure, one whose outermost edge would be crossed by a machine built on Earth, sending back data from the threshold of the galaxy. August 2012 brought Voyager 1 to a threshold no spacecraft had ever crossed. At more than 121 astronomical units from the Sun, the probe's instruments recorded a sudden, dramatic change. The density of charged particles around it spiked by a factor of 40, and the plasma wave system began to detect oscillations at frequencies far higher than those found inside the solar wind. The data told a clear story. Voyager 1 had entered interstellar space, leaving behind the last traces of solar wind for the plasma between stars. Its velocity, 61,000 kilometers per hour, meant there was no turning back. Confirmation came in 2013, after months of careful analysis. The probe's plasma wave receiver, silent for years, picked up the telltale signature of interstellar plasma. An 80-fold jump in electron density measured through the pitch of plasma oscillations. The magnetic field, expected to twist sharply at the boundary, held steady, defying predictions and hinting at more complex interactions at the edge of the Sun's domain. Measurements showed Voyager was now surrounded by plasma 0.08 electrons per cubic centimeter, denser and colder than anything inside the heliosphere. This transition wasn't just another milestone. For the first time, scientists could sample the interstellar medium directly, not through distant telescopes or scattered particles, but with a human-made instrument sending back data point by point. The probe's plasma wave system, designed to listen for planetary radio storms, now served as an ear tuned to the faint vibrations of the galaxy itself. Each oscillation in the data represented a ripple in the plasma that fills the space between stars. In 2017, a new pattern began to appear, a faint, persistent hum, barely above the instrument's noise floor, but steady and unbroken. This baseline tone, hovering near 3 kHz, offered a continuous record of plasma density, tracking subtle changes as Voyager drifted farther from the Sun. The steady signal revealed that interstellar space was not empty silence, but a medium alive with its own quiet turbulence. Crossing the heliopause marked more than a geographic milestone. Voyager 1 had become the first true interstellar explorer, its sensors now tuned to the rhythms of the galaxy. The mission entered a new phase, one defined not by images, but by the music of plasma waves, a record of the invisible, written by a machine still listening in the dark. On May 12, 2025, Voyager 1's plasma wave instrument registered a tone that had not appeared in years of routine data. The signal arrived as a faint, unwavering line at 3 kHz, holding steady hour after hour, then day after day. At a distance of nearly 24 billion kilometers from the Sun, the probe's receiver was designed to catch the smallest vibrations in the plasma that fills the space between stars. But this tone was different, not a burst or a spike, not the echo of a solar storm or the fading tail of a once-in-a-decade shockwave. Instead, it was a persistent hum, so close to the instrument's noise floor that only careful analysis revealed its presence. The signal's constancy stood out. Over the course of several weeks, its frequency barely drifted. The amplitude remained just above background, stable enough to rule out random noise, but too faint to suggest a nearby disturbance. The Plasma Wave System, still operating on less than 5 watts of power, recorded the data in 3-day intervals, compressing each session to fit the shrinking bandwidth allowed by Voyager's aging radioisotope thermoelectric generators. Each transmission took more than 22 hours to reach Earth, its strength reduced to a whisper by the time it arrived at the Deep Space Network's 70-meter dishes. Routine checks ruled out hardware glitches. The instrument's calibration, last confirmed in 2024 after a series of memory workarounds, remained within expected limits. No anomalies appeared in the spacecraft's engineering telemetry. The timing did not match any recent solar events, nor did it coincide with gamma-ray bursts or cosmic ray spikes logged by other observatories. The signal persisted for more than a month, maintaining its 3 kHz signature without the frequency drift typical of passing shocks or the broadening seen during solar outbursts. Mission engineers and plasma physicists compared the new data against the years-long baseline established since Voyager 1's crossing into interstellar space. The earlier persistent hum, first detected in 2017, had shown subtle variations tied to density changes in the local plasma. This new tone was sharper, more isolated, and more stable than anything previously recorded. The data passed through layers of digital filtering and statistical modeling, each step confirming that the tone was real, not an artifact of transmission or software. At Mission Control, the discovery prompted a fresh round of debate. Was this the signature of a new kind of plasma structure, a filament or wavefront undetected until now? Or did it signal a shift in the local interstellar environment, something Voyager's instruments were only now sensitive enough to catch? As the weeks stretched into months, the tone held. For the first time in years, Voyager 1 had heard a new, steady voice in the darkness, a cosmic hum that offered more questions than answers. Engineers at the Jet Propulsion Laboratory began with the basics. Every subsystem on Voyager 1 went under the microscope. Telemetry showed the plasma wave instrument steady, its voltage and temperature readings locked within expected margins. The probe's memory, patched and remapped after last year's data glitch, held up through each diagnostic cycle. No sign of a software loop, no errant spikes from the radioisotope thermoelectric generators. Each check confirmed what the raw data suggested. The 3 kHz tone was not a ghost in the machine. On Earth, the signal's faintness brought a new challenge. Even with the Deep Space Network's 70-meter dishes, the tone hovered just above the noise floor. Engineers ran the data through a gauntlet of digital filters. removing cosmic ray hits, compensating for the slight drift in receiver clocks, and correcting for transmission losses over 24 billion kilometers. The result was a clean, unwavering line, a frequency so stable it could be traced hour by hour, unchanged for weeks. But numbers alone only tell part of the story. To bridge the gap between abstract data and human perception, the team turned to sonification. Frequency values, captured in 3-day intervals, were mapped directly into the audio range. The result was a sound both haunting and strangely familiar, a pure, steady hum, neither rising nor falling, holding its pitch with mechanical patience. At 3,000 cycles per second, the tone fell within the range of a low electronic whistle, audible to the human ear. Each playback session in the lab offered more than just a technical demonstration. It was a sensory connection to a region of space no human would ever visit. The process revealed a subtle but important distinction. This was not the dramatic chorus of plasma oscillations triggered by solar storms, nor the brief, rising tones of past shock events. Instead, the hum persisted, unbroken, like a cosmic dial tone. The instrument's stability ruled out hardware error. The absence of frequency drift or amplitude modulation pointed away from known sources like gamma-ray bursts or solar activity. What remained was a steady voice from the interstellar medium itself, a signal as constant as the probe's own heartbeat. For the scientists and engineers, the moment was both technical and personal. Decades of design, maintenance, and troubleshooting had led to this. A spacecraft, nearly half a century old, still translating the physics of deep space into something that could be heard. In the quiet of mission control, the cosmic hum became more than a measurement. It was the sound of Voyager 1, still listening, still reporting, still alive in the dark. Plasma physicists searching for the source of Voyager 1's steady hum begin with natural explanations rooted in decades of interstellar research. The interstellar medium is not empty. It's a thin, turbulent plasma where density, temperature, and magnetic fields shift across astronomical units. The persistent 3 kHz tone, so stable and unbroken, fits within this dynamic environment, but its exact cause remains unresolved. One leading hypothesis centers on local density waves, gentle ripples in the plasma that Voyager's sensors can detect as changes in electron density. These waves might arise from subtle pressure variations or from turbulence cascading down from larger scales. The signal's unwavering frequency suggests a region of the interstellar medium that is unusually calm, with density holding steady over weeks. Yet, even in the quietest stretches, the plasma is never truly still. Astronomers have mapped fluctuations on scales as small as 0.03 astronomical units, tracing the fine structure of interstellar turbulence. Another possibility involves filaments, narrow, elongated regions where plasma is denser or more magnetized than its surroundings. These structures, predicted by magnetohydrodynamic models and hinted at in data from both Voyager probes, may stretch for hundreds of millions of kilometers. If Voyager 1 has entered such a filament, the plasma wave system would register a stable tone as it moves through the uniform density. The absence of frequency drift or amplitude modulation argues against a passing shock or solar disturbance. Instead, the data point toward a static feature in the local medium, one that persists long enough for the probe to cross it at nearly 17 kilometers per second. Distant shock fronts, waves launched by supernovae, or the collective effect of stellar winds cannot be ruled out entirely. However, shocks typically reveal themselves through rapid frequency sweeps and broadening in the plasma wave data, neither of which appear in Voyager's recent transmissions. The tone's isolation from known solar events, gamma-ray bursts, or cosmic ray spikes further supports a local, rather than external origin. The disciplined approach of the mission team keeps speculation in check. No evidence points to artificial signals or extraterrestrial technology. The hum matches expectations from plasma physics and the known behavior of the interstellar medium. Each hypothesis is tested against years of baseline data and cross-checked with theoretical models. The signal's persistence, its narrow bandwidth, and its independence from solar activity all strengthen the case for a natural, plasma-based explanation. Yet, the precise mechanism, whether a stable density plateau, a filament, or a gentle wave, remains just out of reach, inviting further study as Voyager 1 drifts deeper into the unknown. Signals from Voyager 1 now cross nearly 24 billion kilometers of emptiness, powered by transmitters that draw less electricity than a standard light bulb. At the heart of this feat lies the Deep Space Network, a global web of radio dishes in California, Spain, and Australia, each engineered to intercept a whisper that's 1/quintillionth of a watt by the time it reaches Earth. The largest of these, the 70-meter antennas, stand taller than a 20-story building and weigh almost 3,000 tons, yet must maintain surface precision within half an inch across their entire span. These giants, built to track Mariner and Viking, now serve a probe that's older than most of the engineers who maintain the link. Voyager's high-gain antenna, just 3.7 meters across, beams its 20-watt signal toward home. But distance is a merciless adversary. By the time the transmission arrives, its strength rivals the faintest radio noise the planet can detect. To pull meaning from this static, the Deep Space Network arrays multiple dishes, combining their signals in real time. In April 2024, all 6 antennas at Madrid were synchronized to catch Voyager's faint call, a technical first and a necessity as the probe recedes farther every day. Each session demands precise timing and calibration, with receivers tuned to frequencies that drift by mere billionths as hardware ages and the spacecraft cools. Every command, every data packet, faces a 22-hour one-way journey. A round trip, Earth to Voyager and back, takes 45 hours. Engineers must plan each instruction days ahead, knowing that a missed signal or a power fluctuation could mean weeks of silence. The spacecraft's radioisotope generators have faded to less than half their original power, forcing hard choices about which instruments to keep alive. The high-gain antenna alone now claims nearly all available energy, leaving just enough for the plasma wave detector and a handful of sensors. Each byte of data is filtered, compressed, and checked for errors before the long transmission begins. The Deep Space Network's role has grown with every kilometer Voyager travels. What began as a support system for planetary flybys has become the last lifeline for a machine on the edge of the sun's reach. The team behind these dishes must contend with aging hardware, scheduled upgrades, and the relentless march of entropy. Yet they continue to retrieve science from a signal that is, by any terrestrial standard, lost in the noise. The ongoing dialogue between Voyager and Earth stands as a testament to human ingenuity. A conversation stretched across space and time, carried by technology that refuses to let go. Each year, Voyager 1's power supply slips a little further from its prime. The spacecraft's 3 radioisotope thermoelectric generators, fueled by plutonium-238, now deliver less than half the electricity they did at launch, about 220 watts in 2024 compared to the original 470. This drop isn't just a slow fade, it's a steady, measurable loss, roughly 4 watts every year. The reason is simple physics. As the plutonium decays, it produces less heat, and the aging thermocouples that convert that heat to electricity become less efficient with time. Every instrument, every heater, every circuit on board must now compete for a shrinking share of that energy. The high-gain antenna alone demands nearly 200 watts just to keep its beam trained on Earth. What's left is barely enough to run a handful of science instruments. The mission team faces the same choice year after year: shut down another experiment or risk losing contact altogether. In February 2025, Voyager 1's cosmic ray detector went silent. By early 2026, the low-energy charged particle instrument will follow. Each shutdown is both a loss and a preservation. One less window on the universe, but a little more time for those that remain. Yet, even as the power dims, the spacecraft's legacy grows brighter. The golden record, bolted to Voyager's side, carries greetings in 55 languages, music from Bach to Blind Willie Johnson, and images of Earth's everyday wonders. It was never meant to be a beacon for rescue, just a message in a bottle, cast into the ocean of space. The odds that anyone will ever find it are vanishingly small. But the gesture itself endures, a statement of hope, curiosity, and the urge to reach beyond the horizon. As the years pass, engineers must make decisions that weigh science against survival. The Plasma Wave instrument, now running on less than 5 watts, still listens for the faintest vibrations in the interstellar dark. The magnetometer, housed on a boom to avoid interference, continues to map the invisible fields that shape the space between stars. Each byte of data squeezed from those fading watts is hard-won, a final harvest from a machine that was never designed to last this long. Voyager 1's endurance is fragile, but it's also a reminder of what can last. The spacecraft will outlive its power source, its instruments, and perhaps even the civilization that built it. Long after the last signal fades, it will keep moving outward, carrying a small piece of humanity into the unknown. On May 12, 2025, Voyager 1 registered a persistent 3 kHz plasma wave, an event confirmed by multiple Deep Space Network stations, with signals traveling over 24 billion kilometers and taking 22 hours each way. This marks the longest distance plasma wave detection by any spacecraft, building on earlier findings from 2012 and 2017. Careful instrument diagnostics ruled out hardware faults, and the data was verified using standard NASA analysis protocols. While scientists have proposed several natural explanations, such as local density waves, heliopause interactions, or distant interstellar shocks, no single cause matches the observed duration and frequency of the hum. The limits of current data and Voyager's declining power mean some answers may remain out of reach. Yet, this detection refines our models of the interstellar medium and highlights the global collaboration needed to interpret such faint signals. As Voyager 1 continues operating on less than half its original power, its transmissions remain a testament to human ingenuity and perseverance, carrying both scientific data and the golden record into the unknown.